Open any dictionary. Oxford, Merriam-Webster, the biggest one you can find. Now think about the words people typed on Twitter yesterday. RIZZ, skibbity, delulu. None of them are in there. The dictionary is wrong. Not because it has mistakes, because it's already out of date the moment it's printed. This is the lexicon problem, a core piece of NLP, because every system has to decide, what do I do when I meet a word I've never seen before? And the wrong answer is the one almost every system used for the first 30 years. Last episode, we cracked morphology. Morphemes are the tiny meaning machines that build words. Today, we step up to the whole storage room, the lexicon, the mental dictionary, the list of every word a speaker actually knows, and the list every NLP system has to fake. Here's the puzzle for today. The mental lexicon is not a list of strings. It's a network with shapes, relationships, and most importantly, a frontier. New words show up every day. The system that pretends the lexicon is a closed set is the system that breaks the moment somebody says RIZZ. Today's 3 beats. First, what the lexicon actually is. A network, not a list, hosting relationships you didn't know it had. Second, open class versus closed class, the split that decides which words can be coined and which never change. Third, the OOV problem, out of vocabulary. What does your model do when it meets a word it's never seen? Beat 1. The mental lexicon is a network. When you hear dog, you don't fetch a definition. You light up cat, puppy, bark, leash, fur, bone, all in milliseconds. Psychologists test this. Show somebody the word doc, and they recognize it faster if you showed them nurse a half second earlier. The lexicon is wired by meaning, not by alphabet. The most famous computational version of this idea is WordNet, built at Princeton starting in the 1980s. Every noun, verb, adjective in English organized into synonym sets and linked by relationships. ISA, HASA, part of. A computer dictionary with the shape of a brain. It's still in the standard NLP toolbox 40 years later. Modern systems do not store a network like that explicitly. They store words as vectors in geometric space, and words with similar meanings land near each other. Dog and cat are close. Dog and banana are far. The shape of the lexicon is the shape of that geometry. WordNet was the picture. Vectors are the math. Beat 2. The open class versus closed class split. Some word categories are open. Nouns, verbs, adjectives, adverbs. You can invent a new one any day. RIZZ, doomscroll. These are open class. Then there are closed classes, pronouns, prepositions, conjunctions, articles. You cannot invent a new preposition. The closed classes have not gained a member in centuries. Why does an NLP system care? Because the closed classes are tiny, maybe a few hundred words total. The open classes are huge and infinite. If you're going to build a tokenizer, you can hard-code the closed class words. The open class words you have to handle algorithmically, because tomorrow there will be more of them. Quick sanity check. Try to invent a new preposition right now. A brand new little word that means above but also behind. You can't. Your brain refuses. The grammar of English has a closed slot for prepositions, and your linguistic intuition guards it like a bouncer. That is the closed class wall. It exists in the lexicon, and every NLP architecture has to respect it. Beat 3. The OOV problem, out of vocabulary. The moment your system meets a word it doesn't know. Classical NLP had one answer. Replace it with a magic token UNK. Unknown. Treat every new word as the same gray blob. That meant RIZZ, SKIBID, and a typo all got the same vector. Disaster. Modern NLP fixes this with Subword tokenization. We covered the preview last episode. Instead of storing whole words, you store frequent chunks. Or RIZZ, ING. Z, a new word gets sliced into chunks the model already knows. RIZZ becomes RI plus ZZ. The model can guess at it. We will dive deeper into how this works in the next episode. Today the headline is, the lexicon problem stops being binary. It becomes a spectrum of knownness. But notice the trade. The model never sees the full word RIZZ. It sees pieces. So if RIZZ later becomes a verb like RIZZed, Those are now different pieces from RIZZ. Subword tokenization fixes the cliff, but it introduces a fog. Modern systems live inside that fog every single token. The lexicon problem is not solved. It's just blurred. 3 takeaways before the quiz. 1. The lexicon is a network, not a list. WordNet draws it, embeddings encode it geometrically. 2. Open class can be invented at will. Closed class is locked. 2 different engineering problems. 3. OOV used to break systems. Subword tokenization fixed the cliff but introduced a fog every model lives inside. Quiz 1. What did WordNet introduce that earlier dictionaries did not? A. Alphabetical ordering. B. A. Network of explicit semantic relationships. C. Pronunciation guides. Or D. Translations into 100 languages. B. WordNet's killer feature was the structured graph. ISA links from dog up to canine up to mammal. HASPART links from dog down to tail and paw. It made the lexicon machine readable in a way alphabetical dictionaries never were. Quiz 2. Which group is a closed class word category? A nouns, B verbs, C prepositions, or D adjectives? C. Prepositions. Try to invent a new one. You can't. Pronouns, prepositions, conjunctions, articles, all closed classes. Hasn't gained a member in centuries. Nouns, verbs, adjectives, adverbs, all open and grow constantly. Quiz 3. What's the trade-off of subword tokenization? A. It can't handle short words. B. It fixes the OOV cliff, but the model never sees the full word as one piece. C. It only works on English. Or D. It eliminates the need for embeddings. B. The cliff becomes a fog. RIZZ and RIZZD share 2 chunks, not the whole word. The model has to reassemble the meaning from pieces every single time. That's the trade-off every modern LLM pays in exchange for never hitting an OOV wall. Back to the puzzle. The lexicon is the second place where the 11 layers leak shows up. You cannot decide what a word is without thinking about the layer below, morphology. And you cannot handle a new word without already cheating on the layers above, using context from syntax and semantics to guess. The lexicon is the leaky middle. Next time, tokenizers. The thing you've been hearing me hint at for 2 videos. We open the BPE black box, see what GPT-4 actually sees when you type a word, and watch the moment your text turns into numbers. Hit subscribe if you want it the day it drops.